Good afternoon, everyone. My name is Hen Zhang. I'm going to present a paper, CrowdBind. The other authors of this paper are Michael Roth, Rajesh Panta, He Wang, and Sora Bakshi. This paper is a collaboration between AT&T Research Lab and Purdue University. Here is the outline for today's presentation. I will start with the background and let's take a look. So the first question is, what is mobile crowd sensing, MCS? Taking Take a look at this example. Suppose we want to build a temperature map. Using the temperature sensors on smartphones that deploy at different geographical locations, we can collect the sensor values at different locations. So, in one sentence, MCS is a method of collecting environmental information by coordinating smartphone users at different locations. There are three players in MCS: application, scheduler, user. The examples for applications could be the temperature map as we have seen, or building a city noise map. A scheduler is one example, our paper, CrowdBind, and users are users who sign up for mobile crowd-sensing campaign. Next, I'm going to talk about the challenges as well as the challenges we are going to solve. So for MCS applications, they want to maximize the task coverage because tasks are accomplished by the users. Also, they want to reduce the data collection cost because the application sometimes need to pay the users for contribution data. And for MCS users, they want to maximize their reward or incentive, and they want to reduce their detour because some tasks may ask a user to go to some place that are out of their daily routine. And the smartphone energy cost needs to be reduced as well because users do not want the application to drain their smartphone battery. But what about task fairness? First, let me define it. So, task fairness refers to whether MCS users receive fairly equal number of MCS tasks. Ideally, we want these users to receive same amount of tasks. We use Gini coefficient to measure task fairness, and Gini coefficient lies between 0 and 1. 0 means the fairest distribution of the data, and 1 is the most unfair case. So knowing what task fairness is it important in mobile crowd sensing? We conducted a survey to answer this question. So in this survey, we asked 96 students, and then for these people, we assume three different models, and under each model, we ask them the same set of questions. The three models are volunteer, subscription, and pay by work. Volunteer means users do not get paid, but they will get any information they want by sending some mobile processing tasks to other users to accomplish. For subscription model, user get paid for a fixed period of time, and during this fixed period of time, each user get paid the same, and each user may receive different amount of tasks. Pay by work model says that users get paid in proportional to their contribution. And the questions we ask are, do you think this model is fair? And if you feel it's unfair, will you drop it? Or you do not even want to participate in the mobile crowd sensing? And the result turns out that people do feel each of the model have certain percentage of users feel the model is not fair. For volunteer and subscription models, that's not a surprise. But for pay by work, since people get paid in proportional to their contribution, we think that people may feel it's fair, but it turns out 1/3 of users still feel like this model is not fair. Also, to compare the importance in MCS between fairness, energy consumption, detour, and reward, we ask people to rate each of those four metrics as very important, not important, or do not know. And turns out fairness has 80% of users who rated fairness as important or very important. This number is roughly similar to the other three metrics. So in conclusion, we think that MCS users do care about fairness. However, current literature only mention it is a desirable feature, but not optimized for that. So in summary, CrowdBind is the first MCS scheduler which optimizes task scheduling fairness without degrading two other primary objectives: task coverage and the average energy cost. We proposed two variant greedy algorithms to solve this fairness problem, and we evaluated CrowdBind using a real-world user study of 50 students and a simulation of 90,000 people for the scalability study. Our mobility trace is available in this link. So let's talk about a motivation example. So before that, I will define two terms: task. Task is the issued by the MCS application and completed by the users. In the task needs to specify sensors, location, what is range of this performance, and number of users needed, and what time the task needs to be performed, and what is the periodicity. And the task instance is created for each period of a task. Let's take a look at the example. Suppose a MCS application issue a task of collecting temperature values around our conference building. It asks end users to report the temperature every hour from 8 a.m. to 10 a.m. Then two task instances are created. One requires user to upload before 9 and another one before 10. And we also have task coverage. It's average coverage among all instances of a task. N here stands for the total number of task instances of a given task. Si is the number of actually selected users for that instance I. And MDR is the minimum device requirement, and that stands for the minimum number of tasks required by each task instance. And given from the previous example, we say suppose each of the two task instances has a MDR of 4, and if both eventually select 4 users, which means S1 and S2 are 4, then the task coverage is 1. But if first instance is only find 2 users, which means S1 equals to 2, the coverage eventually reduces to 0.75. Now we talk about the 5 features that drive the design of CrowdBind. First one is late binding. Suppose a task is submitted on Monday and it requires 1 data upload every day for 1 week, which means there will be 7 instances of tasks. So instead of scheduling all the 7 instances on Monday when the task is submitted, we can schedule each instance maybe 10 minutes before the task instance needs to be performed. Delay tolerance, it says that to take the sensor value, it can be taken now or can be within the next 10 minutes or 20 minutes, and the values will not differ too much. And spatial tolerance means that we do not require user to go to a exact coordinate to perform a task. Rather, the user can stay in a region, let's say a circle with a radius of 100 meters, that's satisfiable. And the fourth feature is that users have regular mobility pattern, which means we can predict where the user will be when some tasks are happening in the future. And given the user study mobility trees, we build a trajectory-based mobility prediction, and our result is shown in this figure. The deeper the color is, the more accurate the prediction is. So given the x-axis is a historical data, mobility data, and the y-axis is how far ahead we are predicting, 10 minutes ahead, 20 minutes ahead, etc. And the takeaway from this point is that given more and more historical data, the prediction is getting better, and if we are predicting too far ahead, the prediction accuracy reduces. And the last feature is look ahead, which means we will schedule multiple task instances in a certain look-ahead window. For example, 20 minutes ahead, we will schedule all the tasks in this 20 minutes. That's the feature we use. And let's take a look at the illustrative example. Here we have 2 task instances and we have 4 users. And the dashed line here means whether the user is available for that task instances or not. And each task instance requires 2 users. We easily say user 1 is available for task instance 1, partially for task instance 2, user 2 and 3 are available for task instance 1, and user 4 is available partially for task instance 2. Without a mobility prediction look ahead, what could happen is task instance 1 find 1, 2, 3, the 3 users are available, it will randomly choose 2 of them, and task instance 2 find user 1 is available, and task user 4 is available as well, then it will choose user 1 and 4. So then user 1 may be picked twice, because for task instance 1, it may choose user 1 or not. But with CrowdBind, we have a mobility prediction and look ahead. We can deterministically reserve user 1 for task instance 2 because we know task instance 2 is in the look ahead window, and we predict user 1 and 4 will be in the region of task instance 2. So eventually we choose 1 and 4 for task instance 2 and 2 and 3 for task instance 1. So in this case, our selection is fair because each user is selected once. Now let's talk about the CrowdBind design. Here, the CrowdBind server is in between the MCS application and the clients. And CrowdBind server has different modules. The key module is device selection module, which our core greedy algorithm is implemented. Before we go to the algorithm, let's talk about the problem first. And user selection problem is a well-known problem in MCS. It's known to be NP-hard, and we formulate a minimization problem to solve it. We have three subjection constraints, and the first one says that for a user selected for a task instance, it has to have enough number of battery, which has to be larger than a threshold, MBR, which is specified task. MBR could be 80%, which means if a user has battery lower than 80%, that user will never be considered. A second constraint is that the user selection has to be the fact that the final selected number of users of one task instance has to be equal to the number of required users for that task instance. A third constraint is more complicated. We can refer to the details in the paper, but at a high level, we think it as the predicted number of available users of a task will be greater or equal to the minimum required number of users for a task. Recall that the minimum required number for a task is the sum of minimum required number of task instances, minimum number of users for each task instance of the task. And we're trying to minimize the Gini coefficient of the usage of the users that are in the consideration look-ahead window. So the two greedy algorithms are GRandomX and GHeuristic. They have different initialization phase, but they have the same optimization phase. The key to optimize fairness is that we look ahead and look all the instances within the t minutes. We predict the available users and we map those available users to those task instances so that the user's usage ultimately will be equally distributed. So the GRandomX initialization. So X stands for how many X rounds of execution with different random initialization seed, and in each round, the initialization will randomly select MDR number of users for each of the task instance, and then followed by the optimization stage to satisfy the constraints in the problem formulation. And then, out of these X execution rounds, we will choose the fairest selection of the users for the task instances. For GRandom heuristic, it only executes once, and the initialization is more complex in the sense that we want the initialization to help the optimization phase so that the user selection will be faster to the global optimal or the fairness selection. The key to this algorithm is that for each task instances, we weight the users based on different properties. Those properties include mobility, predictability, sensor integrity, probability to accomplish a task instance, and the usage history of the user. There are more technical details, please refer to the paper. And the optimization stage is used by both algorithms. After initial selection, we have initially selected a set of users for each task instance, and we will look at the metrics of the constraints of the problem formulation, and will greatly replace some of the selected users in the initialization selection with some other users that are not selected, and the ultimate goal will be if we cannot find a better replacement, then we stop this optimization phase. Also, technical details are complex, but please refer to the paper for them. Here we compare the performance of GHeuristic and GRandomX. We compare heuristic, random 1, random 5, random 10, and random 20. We measure the running time of the algorithm, the Gini coefficient achieved, and the task coverage achieved. In total, we have 9 tasks here, and we execute those 9 tasks 100 times to draw statistically valid result. So the takeaway message here is that GRandomX runtime is proportional to the number of rounds, and when the round is greater than or equal to 10, the GRandomX is more fair and has higher coverage than heuristic. Heuristic has relatively good performance and is fast. Also, the larger the X, the more likely the GRandomX algorithm will approach the global optima, because the GRandomX algorithm is trying different initialization points in the solution space with the hope that some of the random initialization will lie to the position that are close to the global optima, and it eventually goes to that global optima. But the heuristic, maybe it will be initialized to some local optima, which is very close to the global optima, but not that good. So now I'll talk about the implementation and the evaluation. So we have two parts. The first part is user study with 50 students and 1 month of study. We receive the location and we send 213 tasks with 3,916 task instances. We compare CrowdBind with 4 prior works: periodic as a baseline, PCS from Census 13, Sense8 from middleware 17, and Crowd Recruiter from Rubicon 14. The key for the periodic protocol is that once a task is received, it will send the task to all the users, which is 50 in our user study, and all the 50 users will check if themselves satisfy the task requirement, and the user will decide whether the user needs to perform the task or not. PCS send only to MDR number of users, and the key for PCS is to optimize the network stage of the data uploading. Sense8 optimizes both the data uploading stage as well as some sort of simple fairness measurement, but that measurement is too trivial and is not that good. And Crowd Recruiter is a method to reduce the number of users that are involved. It tries to use one user for multiple tasks. The rationale behind that is they pay the user the same amount of money for a period, which means the less users selected, the less payment the application will pay to the users. Each protocol in our user study is a standalone Android application installed by the users. In our simulation, we use a Gowalla mobility dataset with 90K users, and we only use 1 month of the mobility data, and we synthetically generate a lot of tasks at different locations and to perform the scalability study. So here is the simulation results, and we compare the prior work and baseline. For the task coverage, we want it as high as possible. Gini coefficient, we want it as low as possible. Also, average energy cost, we want it as low as possible. We are changing the task radius from 100 to 1000, which means task radius higher, we are more likely to find available users for a task. So we found that the CrowdBind performance, the two algorithms, achieve near optimal task coverage. The optimal task coverage can be achieved with periodic. That's a baseline because periodic sends the task to all the users. Whatever the ground truth is, the periodic protocol will find it out. And the other 3 protocols, they send to MDR number of users, but because they do not predict the location of the user, their task coverage is lower because they cannot find some moving users. And also for Gini coefficient, we optimize Gini coefficient, we have better fairness measurement, and because our protocol is fairer compared with others, the average device energy cost for our protocol is also lower. But for periodic, since it has relatively good fairness measurement, because it sends the task to all users, which means each user may perform relatively similar number of tasks. But the problem is those users perform too much tasks, which result in a high average device energy cost. So in summary, CrowdBind algorithms are the fairest, cost the least energy, and achieve near optimal task coverage. And our user study results are consistent with those in the simulation. But also in the paper, we also changed the delay tolerance and MDR. You can refer to the paper for those evaluation results. So in conclusion, the key to our CrowdBind is that we allocated the task instances to as many users as possible so that the inequality of usage and the average energy cost of each user are reduced. And we do not damage the task coverage because we can predict where the user will be and look ahead for the task scheduling. So this is all of my presentation. I'll be very happy to take any questions you might have, or you can, if you have any further discussion, you can shoot an email to the email address provided in the slides.